Thank you, and thank you for having me tonight. First is sound-wise. How is that? Good? Okay. Oh, I never know. From one auditorium to the next, you need to get a sense of how to project the voice. So good. So tonight we'll be talking about two different topics. And guess what? Just for interaction, there will be a Q&A in the middle of the talk, just so we get to make this like more interactive than just a lecture. So we'll be talking about the search for life, especially around other planets than our own, and in fact around other stars than our own, which are around exoplanets, extrasolar planets. And then I'll talk to you about another topic that's close to my heart for about 2 years now, which is planetary defense, which is different from planetary protection. Planetary defense relates to getting to map out asteroids that could be impactor and that could affect life on our own planet. Okay. I do like to start my talk by presenting takeaways first, in case you have to miss something, having to go to the bathroom, for example. And the takeaways from the talk will be, first, that those exoplanets that I just mentioned, they are key because they provide new insights or new vantage points with regard to key concepts to ourselves and our societies, ranging from how we relate to climate, resources, to at some point life and even maybe intelligence. Okay? So it's important to diversify those vantage points, and that's exactly what exoplanets are for. Second, the way we get to these exoplanets and these new vantage points really relate to technological developments. The rate of our technology just keep on accelerating, and through them we get new windows into space. And I'm going to talk about these new windows specifically for the field of astrobiology, search for life, as well as, again, planetary defense. And then the last, but I think most important takeaways, is that now that we have these new drivers, exohabitats, planetary resources, I'm thinking here in space, manufacturing, and so forth, it really seemed like humanity within the next century will be making its next big step in our own space odyssey. And by that I mean truly become an interplanetary species. Okay? So long story short, space is calling, or has been calling, and humanity is now finally ready to respond, and we will make our stand soon. And when I say soon, for the young people in the room, that's definitely for you guys. So listen up. And making our stand, sorry. Actually, we just talked about nanotechnology and the prospect of extending lifespan significantly within the next decade. So for anyone in this room, stay tuned. And when I say make our stand, I do like to relate that directly to Carl Sagan, last quotes in his Pale Blue Dot speech, because Earth really is where we make our stand for the moment. There will be another time far into the future where it will be time to make another stand, but that's not related to this talk. So I'll split this talk into two parts. Part one, get ready to stumble upon life elsewhere. And I'm going to talk about the different actors in this space odyssey. The new sirens are exoplanets, attracting us to them, thinking about other life forms and other habitats. The hero is new technology, specifically JWST. And then we do have chimeras, some bottlenecks, some challenges that we need to overcome, and that will be related to our current worldview, specifically with regard to light-matter interaction, because we need to translate spectra into information with regard to what's going on out there, as well as stellar models. We'll get to that. Once we've talked about that and how we are tackling them, I'll let you know about a whole new plot line for this chapter that we've designed to be able to do habitability assessment within this decade. Every other plot line related to waiting for another round of observatories, we bypass that. We'll take questions so that we can engage a bit. And then we move to part two, where I'll talk to you about how we use observation of exoplanet to study our own solar system for free, and demonstrate that JWST is, in fact, an excellent asset for planetary defense. I'll talk to you about the case study we did with potential impactor 2024 YR4. And then, for the fun of it, that's just a tag-on that I added after, we'll talk about in-space mining and the new industrial revolution that awaits. All right, let's get going. Part one, stumbling upon life elsewhere. As I was introduced, I was lucky enough to be part of the team that found the TRAPPIST-1 planets. You may remember them, you may not, because so much happened since 2017. Those are the first planets that have this winning combination of being terrestrial, so rocky, temperate, so potentially habitable, and found around the right kind of star such that we can study them with current technology. The consequences of that? We were all over the news, and it is estimated that about 2 billion people got to interact with that discovery. Now, was that expected? I mean, I didn't. To be honest, I thought that this level of engagement of the public would be associated with finding life elsewhere. But it seemed like our relationship to Spain runs to space, Spain too, maybe, but space runs so deep that we get to capture the public's attention simply by finding rocks that allow us to make the search for life tangible. Okay? And it makes sense. I mean, we've looked at space to cross ocean, to plan for the timing of our plantation, to predict the coming back of fish upriver. Space has been there to nurture a relationship to this world from the very beginning. And so at times we ask profound questions such as, where do we come from? How did we get here? It does make sense that when we find the first planets where we could finally search for life elsewhere, we get a third of the population engaged. Now, the point I want to make here is that this discovery isn't that surprising. The pace at which we have been awakening to the universe has been increasing simply as our technological development has been increasing. And so that small step isn't just a step. For me, it is a reminder of how close we are getting to an answer to some of these key fundamental questions. And with that in mind, I think that really we are on the verge of stumbling upon life elsewhere, be it under the crust of Mars, under the ice crust of Enceladus or Europa, in the clouds of Venus, for those who know what's going on in Venus right now, or on a planet like TRAPPIST-1. It seems like within the next decade or so, this is what's on the menu, stumbling upon life elsewhere. It really feels inevitable. And for me, to really just crystallize this concept that this is inevitable and the relationship with the pace of our technological development, that year, 2017, is a perfect example. Because on the year we found the TRAPPIST-1 system, guess what happened over the months that followed? Humanity discovered the first interstellar object, an object coming from out of space, well, out of our own solar system. And the first gravitational waves were detected, while predicted over 100 years ago, right? It's not just terrestrial astronomy that kicked in. This field just moved on. And so it is clear that we are awakening more as well as faster. And as a result, I really believe that we are getting increasingly closer to this key step on our odyssey, which is stumbling upon life elsewhere. So now to me, the big question is not if or when, but rather, okay, that's going to happen. What are we going to do about it? Really, what are we going to do about it? At a time where we're facing so many challenges, AI is going to be replacing a large fraction of the job that we have. What are we going to do of the news of a discovery that can capture such attention worldwide? Again, 2 billion people just for these discoveries of rocks that may or may not be habitable, but really finding life elsewhere. And so starting in 2017, I've had the chance to give quite a few talks to social, political, industrial leaders, facing them with that question. Are we just going to be letting this fleet between two tweets, or are we really going to harness the transformative power of getting the first tangible answer to those questions? And I really like to relate this discussion to this quote from Carl Jung, the father of, well, you know Carl Jung, because being a conscious being is directly connected to the worldview that you've built over time. And that worldview, you can call it physics, you can call it biology, it's really just a model of the world out there. And as we go and explore the universe, we get to reshape, transform our worldview. And because we co-evolve with that worldview, we humans change too. So if a third of the population can be captivated by the revived prospect of finding life elsewhere, imagine again the power that is held in the news of having found life elsewhere, whatever it is. And to connect to that, when Copernicus claimed that the Earth was not at the center of the universe, it triggered a revolution, right? A revolution through which religion, science, and society had to adapt themselves to this new worldview. So with this in mind, and what has happened since 2017, I brought that back to MIT and started a new class, our Space Odyssey, where we study this relationship between humanity and the key development or learning that we've gained with regard to space throughout time and culture. We're not going to go much further out with this tonight, but I just wanted to give you the context for what comes next in this talk with regard to exoplanets. If you want to learn more about that, just stop by after. I'll be here for a good chunk of the night, happy to chat more about this aspect. That tells you why I started to do what I'm doing. And the potential for exoplanetary science, not just finding other planets and studying other climate, but truly reshaping how we see ourselves and how we relate to our environment and the universe. Now that this is said, for the background, let's dive to the first step, exoplanets. These worlds that are far away, but actually not so far away. The sirens, the new things, dragging us into space, at least from an intellectual point of view. So why do we care about them? Believe it or not, everything we know about planets, planet formation and so forth, or have known, because things are changing now, has been based on one unique sample, the solar system. Right? For centuries, we've studied these planets with or without depth, it depends on which we're talking about. And naturally, what we got to learn about planets was limited, right? It's one sample. Think of 8 planets. Think about picking 8 people that you may know well, and these people happen to be coming from the same family or same town. And now you want to predict the outcome of, say, a political election. These are different people, but they are from the same background. They share history, values, and so what they can help you with regard to this prediction is limited. Similarly, what we can learn from these 8 planets formed around a 3rd generation star 4.5 billion years ago about planet as a whole is limited. So when we started finding planets around other stars than our own, we found things that were completely unexpected. For example, we thought that gas giants like Jupiter, Saturn would be formed far away from their star and just be there, right? When I say far away, Jupiter is so far away that it takes about 11 years for it to turn around the sun versus a year for Earth. The first exoplanet that were found, and in fact the bulk of exoplanets that were found since the first one in 1995, so let's say 1995 to 2005, were gas giants just 3 days away from their star. They were so close to their star that they would be turning around their star in just 3 days, again, against 11 years, right? Creatively enough, we call them hot Jupiters because they are so close to their star that they are typically the thousands of Fahrenheit. But that's not it. As we moved on, we found planets without star, literally free-floating in the galaxy. Planet with multiple stars, like Kepler-16b that has 2 suns and offers this iconic double sunset like Tatooine in Star Wars. Right now, the record is 4 stars in the sky of a planet. We found planet with 37 rings, about 200 times the extent of Saturn's rings. So big that if Saturn had such ring, it'll be bigger and brighter than the moon in the sky. We found planets literally dying next to their star, being pulled apart by the gravitational field of their star. That's how much diversity we found. Nothing like what we see in our own solar system. And that is the power of exoplanetary science, bringing these complementary vantage points. Now, how do we detect or study these exoplanets? I don't know about you, but when I think about planets, I think about spatial features. I think about the ring of Saturn, the zone and band of Jupiters. And I'm sure you've noticed that I've used a lot of posters, beautiful graphics from artists. And that's due to the fact that there is really not much I can show you with exoplanets. Like, this is an exoplanetary system right there at the center. And I can take the bigger telescope we have to zoom in, and everything I got for you is just one bright dot. And so everything we do is data science. We do use data to extract information about the star and whatever else may be hiding behind these few pixels. What does that look like? That bright dot has a flux that changes with color or wavelength, as well as time. And I'm going to use these two dimensions to introduce you to the two main detection techniques. The first one is called the radial velocity technique, and it's based on the Doppler effect. You've all heard an ambulance coming towards you and then away from you. As the ambulance comes towards you, the pitch gets higher, and then as it moves away from you, it gets lower. Same thing with the emission spectra of the star. As the star is not rotating upon itself, but it's also orbiting a common center of mass, as we see here, because it has a companion, the star is moving away from you, so its pitch is lower, it gets to the red, and then it comes towards you, radial velocity, and it's shifting to the blue. Okay? The oscillation of that spectrum to the blue, to the red, gives you the orbital period, and the amplitude of that oscillation tells you how massive the companion is to be able to pull the star in one direction and then the other. Now, the other technique, which is the dominant technique now, is a transit technique where, again, we don't see any of this, but we get the flux of this whole ensemble of pixels. If something passes in front of the star, you have a flux drop, and that flux drop is periodic, you get the period, but it also is related to the planet to star area ratio, so you get to say how big the planet is with regard to the star, so you get a size. Moving in the 2005 and onwards, more and more planets were found with both techniques, so we could get the mass and the size, so we could talk about density, so we could start talking about what are they made of. Are we looking at a big giant ball of iron, say a puffed up version of Mercury, or something that's more like a gas giant, lower density? Fast forward, and this is really what I'm excited about and what I've done my PhD work and so forth, we could start having enough information that during the transit, we could disentangle the tiny bit of light going through the planet atmosphere to perform what we call transmission spectroscopy. Now, what is transmission spectroscopy? That is transmission spectroscopy done with your brain. Some light is going through each of these components or contents, and just by looking at the color, you get to infer what this is made of. That's transmission spectroscopy 101 right there. What does that look like for exoplanets? For different colors, the tiny atmospheric annulus may be opaque, masking the star, or transparent, and the light can go through, which means more of the star is blocked, or less. And so the transit depths get to change with wavelength. And when you do that with enough colors or wavelength range, you can look at these kind of plots. This is one of the first transmission spectrum of an exoplanet in the 2013, where we have data from the Hubble Space Telescope that show that the planets seem to be masking more of the star, around 1.4 micron, revealing here a features of water, right here. So this is transmission spectroscopy level 1, where we get to reveal absorption features of molecule, with Hubble 2013 and onwards. Now, in our story, we have a hero that comes in and changes again, the James Webb Space Telescope, $10 billion facility, truly designed to do this kind of science. Most of the science we've done so far has been with facility, not really designed to do exoplanetary science. What does that mean? We have a much larger telescope, so we have exquisite data quality compared to what we had before. You'll see that in a second. In addition to that, it allows us to reach a much higher spectral resolution. You'll see that in a second as well. And most importantly, it's covering part of the color range or wavelength range that truly matters to infer a wide range of properties, especially when it's time to look for molecular feature. So let's really look into this transformation, this jump with regard to information contents. What you see here is a transmission spectrum of one of the first exoplanets observed with JWST, and that reveals these very strong features of carbon dioxide right here. Right? The transit depth is deeper, the planet appears bigger because there's carbon dioxide here that allows for the atmosphere to be opaque at much higher pressure level, a much lower pressure level, basically. So now let's take that and compare it to what we had before for the exact same exoplanet. What you have here is Hubble data. Here it's Spitzer data points. Spitzer is a heliocentric space telescope that has been decommissioned since. And let's add that spectrum right here. Obviously, we have data for that exoplanet all the way out, but I'm going to just keep these two to compare. What do you see? First, higher spectral resolution. Do you see the number of points that you have here? How well you can sample this CO2 feature? And then look at the precision on these many, many more data points. So we have better spectral resolution. We get to cover all of that spectral range and much better precision, which means it's changed again. We can do the kind of thing I was looking for to do as a PhD student. We can go from simply saying this bump is CO2, this bump is CH4, so molecular identification, and really go one step further, which is to say, wait, the light from the star is interacting with methane, but that's how much methane is there. That's the temperature at which it's interacting with light and the pressure level at which it is interacting with light. In other words, we can really decrypt the spectral information and talk about what is actually going on out there, not just say, oh yeah, there is this, but how is that happening? So let's go back to our example where I don't see orange juice, but let's say you see someone with a glass in which you have an orange liquid. Now, is it orange juice or mimosa? Is this orange juice? And if so, how is it diluted? Is it lukewarm, cold? This is what I'm talking about. Your brain can do transmission spectroscopy level 1. It cannot do the kind of thing that we are working on, or actually doing now, with exoplanetary atmosphere, which is really getting to know how much of each compound, what temperature level the interaction is happening at, and so forth. And it's key. If you want to talk about habitability, you want to know how much water is there, or whatever compound is there as well, and then at what temperature the absorption is happening. If it's not temperate, clearly, it's not going to be a habitat. Now, what's limiting us? What's limiting us right now can be folded into two categories, but both of them relate to models. I'm not going to go too far into those details for the purpose of this talk, but I still wanted to let you know really what we're looking at. First, light-matter interaction. We know how light interacts with some molecules in settings that are typically close to the settings we find on Earth. For example, we know how carbon dioxide interacts with a bulk of wavelength range, but when it's in a background of nitrogen or carbon dioxide. We don't know how carbon dioxide is interacting with light in a background of hydrogen. And yet, what I've showed you before, right here, is exactly that. It's a beautiful carbon dioxide feature for a gas giant, which means a background gas, meaning that there's a tiny bit of carbon dioxide in a whole bunch of hydrogen molecule. And so translating that into temperature, pressure, everything I've said is actually challenging because we don't know well enough how this carbon dioxide behaves. And that's not new, right? Already in the 2005, when people were trying to study Jupiter in greater depth, they realized that the extent to which they could constrain how much oxygen is within Jupiter is limited by how well they know how water in Jupiter is behaving. Okay, so already then, they understood that their understanding of light-matter interaction was a bottleneck to truly translate that remote sensing data. And so for planetary science, what it looks like, and I'm not going to bore you too much with this, but basically, let me walk you through that. What we're looking at here is different curves that gives you a confidence interval for different opacity model, so model that tells you how light and matter interact. What are they saying for a given spectra is the true amount of CO2 in one exoplanet atmosphere. Width of these confidence interval relate to the capability of the instrument. In other words, independently from the model used to translate the information, the width of the confidence interval is 0.2 dex. You don't even need to know what the 0.2 dex units are. What matters is the difference between the precision the instrument can reach and the discrepancy between models. If we were to do that with Hubble data, you would see confidence intervals that are much broader than the spread that we see with opacity models. In other words, it wouldn't matter. Like the models would be good enough to translate Hubble data. We've now reached a point where the instrument JWST can perform to such a level of precision that we have to start caring about our understanding of light-matter interaction because they are driving the uncertainty budget. We have moved from an era of instrument-limited science to an era of model-limited science. And so we have to go back to the blackboard and use basically quantum chemistry and quantum physics to better understand light-matter interaction in a way that is scalable. If not, we're basically going to be in an opacity-driven regime. And that's the accuracy world, while this is where we could be performing orders of magnitude better. Now, again, as I said, there are a couple of ways to handle light-matter interaction. We can do lab measurements. It's great. That's what we've done for 40 plus years. But now, thanks to high-performance computer, we can turn to quantum dynamics and produce the result that we need in a matter of weeks, even though we thought it would take 6 months, and in a way that's scalable. And if you want to know more, I'm happy to talk more about that later. Because I want to turn to the other part of these chimeras, which is how well we know stars. And the answer is not well enough. When a planet passes in front of its star, the star is not uniformly bright. There's spots, facula, flares. And what happens is that when we observe the planet transiting, there's both information about the planet and information about the star creeping in together into that transmission spectrum. What it means is that the only way to disentangle between both contributions is to improve our stellar model. And in the meantime, we're stuck with this. Press releases where we say, hey, we found water, but we actually can't say if it's from the planet or the star. And again, if we want to talk about habitability, we kind of want to know that that water is on the planet. Now, don't worry too much about it in the sense that we've done a lot of work on this with my group over the last 6 years. And of course, the community has too. And we found a couple of solutions to handle the problem. And so for the purpose of this talk, let's assume that this is completely solved. And so the search for exohabitat is unlocked. I told you before that with current technology, the previous pathway to assess for habitability and inhabitability are not within reach. And so I'm glad to report that we have worked on a revised plotline to make this accessible with current technology, and this within the next decade. So we're going to go back to TRAPPIST-1 and walk you through the steps here. This is TRAPPIST-1, brought to scale with regard to our solar system. This is where TRAPPIST-1 would fit. It's a highly compact system, twice as old as our own, and it's really a Swiss clock. For this to be stable on such scale, everything needs to be in perfect resonances with each other. That's also something we can talk about later. The first step we had to do was to confirm that those planets did not manage to keep their primordial atmosphere. Primordial atmosphere is hydrogen, helium dominated. That's what planet gets together when they sweep the leftover of the planetary disk. Again, hydrogen and helium. They cannot keep it because that means very strong greenhouse gas effect, which means temperate planet would actually not be temperate planet because of the greenhouse gas effect. So we don't want that. I was lucky enough to take the lead on this, connected with a Hubble director at the time, pointed Hubble to these first terrestrial planets in 2016, 2017, and showed that we're good. They don't have this. And then we needed to wait for JWST to search for whatever else that could be having, some thinner atmosphere that could actually allow for habitability, or something else. And so in the meantime, I brought the community together and designed a roadmap that would account for everything that could happen to bring us as soon as possible to completing the exploration of those planets with JWST. We're not going to walk through this whole thing. That's not going to be interesting. But I'm going to attract your attention to two parts, this one and then the top left later. What we have here is what we wish will happen. It's a point where we find an atmosphere, and then we find something intriguing in there. We spend even more time, say, a couple of years on the system, and then we can say it's inhabited or habitable, one or the other. Inhabited means there's life form, whatever that is, and then habitable means there's liquid water. So it's habitable from our point of view, water being the key solvent for our own chemistry. So what you see here is something new. I'm not looking for oxygen, I'm looking for depletion of carbon. And that's the twist. The twist here is that we found a new avenue to assess for habitability, again, with current technology. Typically, when we think of habitability, we think of things such as an ocean glint, right? It will mean that if we look at the system, there will be an angle where if there's ocean, you have a peak in brightness that relates to the reflection of the stellar light on the ocean. And we've done that in the solar system. What you see here is the light from the sun reflected on one of Titan's lake. It's not water, it's methane lake, despite the fact that Titan has this very thick atmosphere of nitrogen. For inhabitability, everyone would think of oxygen, right? Earth's oxygen level is at 21% in the atmosphere, owing to the fact that life has pumped that up through different phases of oxygenation. The issue with oxygen, though, is that oxygen is a compound that can be produced by various geological processes, and to really say oxygen is for sure a sign of life would require understanding planets to a depth that is not possible with current technology. And on top of that, oxygen is a pain to detect. Oxygen is a very simple molecule, 2 atoms, it's the same, linear, so it doesn't interact with light really well, to the extent that I'm going to tell you that oxygen has some signature hidden there, and those signatures are these tiny lines, so not really accessible with current technology either. So during my class at MIT, I've been showing this plot over and over again. And then I realized with a friend that this was a key. When we look at the solar system, we have the atmosphere of Venus, Mars, that are pretty much similar. And Earth is the oddball. And it is an oddball, why? Because CO2 is missing. Now, where is the CO2? Why is it not in the picture? And the answer is pretty obvious. Because we have liquid water. CO2 dissolves wonderfully in liquid water, and the strong water cycle on Earth, I'm thinking here ocean, but also plate tectonics, bringing the carbon into the crust and the mantle, is what allowed Earth to clear out its atmosphere. So the twist here was not to say, hey, let's look for things that water cycle add to the system, a glint, or life add to the system, signs of oxygen, but also instead, look for something that is missing. And that was the paradigm shifting thinking here. Now, in case you don't know, I thought it was relevant to add this. It is believed that Venus was habitable, that there was a time where there was enough water on Venus to clear out the carbon dioxide from its atmosphere and store it in. Same thing for Mars, okay? So there is a time dependence to these processes. What you see here in yellow is the volcanic activity of each of these planets, and in blue, the presence of liquid water. And there is a relationship between the capability of a planet to sustain plate tectonics specifically, and the amount of water. And that relates to water being in the crust, as well as carbon, because carbon is a great lubricant for plate tectonics. So we're really thinking here about large-scale cycles. It's basically the Gaia hypothesis. So, long story short, as I said before, we realized that instead of looking for what is added to the system, we had to look for what is missing. And what is missing is primarily rooted in carbon dioxide. And as you've seen at the very beginning of this section, carbon dioxide is really, really well suited for JWST study, because it is in fact the first molecule that JWST discovered in an exoplanetary atmosphere. So that makes the search for life within reach with current technology. And that brings us to the end of section 1. So I'm happy to take 2 to 3 questions before we dive into planetary defense and asteroids.
The use of quantum mechanics in order to look at the light, spectroscopy, whatever. What exactly were you doing with quantum mechanics in order to do that?
Yeah, great. Thanks for asking. So there's 2 steps in this. Let me just see if I can showcase this. The first step is to ask ourselves, given the current precision of the instruments, how well do we need to know the range of properties of these systems? For example, a molecule has hundreds or billions of line or energy level that it can use to interact with light. Each of these energy levels have a broadening, like a line shape that we need to know. That is this here. To date, for carbon dioxide, we have huge uncertainty of the order of 100% or more. And what we had to estimate first is how well we need to know each of these parameters to make sure that we go back into a regime where JWST is the bottleneck, so we're instrument limited. And then we had to design the experiment to make sure that we fit models. And that, to answer your question, requires us to go from like literally modeling from an ab initio point of view, these molecules, their electronic structure, and then the interaction with the wavefront. So these are each of the steps that needs to be done to do that properly and get to the cross-section. Yeah? Yes?
If we're going to go to Mars and terraform it,
Excuse me?
if we're going to Mars, we'd have to terraform it, I take it. Would this have to use a...
If we were to go to Mars, we had to terraform it. That's
I take
a question.
it if you want to live, but using this kind of analogy, this plant, would we have to use a greenhouse effect, I take it, to produce it, no?
So the different approach to going to Mars and settling in usually requires, at least to date, requires creating small-scale habitats. It will not be planetary scale. And that relates to the following here. The fact that Mars is such a small planet that it lost its atmosphere relatively quickly. So sustaining an atmosphere on a low gravity object like that would be challenging. Creating small-scale habitat that we can control is the most likely option. So fully terraforming Mars will be a loss in the sense that it would keep on losing its atmosphere. So you would have to find ways to replenish it with volatiles. So likely not an option. Does that answer the question? Yeah. Good.
Well,
in other words, if you have a timeshare on Mars, you'll be staying inside.
You showed the one bright dot, and you talked about the Doppler effect and being able to think about planetary motion inside it. Did you get all 5 of those, or how many objects you found? Was that all from one spot like that?
For the TRAPPIST-1 planets,
Yeah.
these were actually found using the transit technique. So this, right? They were found around a star that is basically the size of Jupiter.
Yeah.
And that's what I meant earlier. The third quality that they have is that they are found around the planet, around a star that is good enough. To study small planets, you need to be around small star, and they are found around stars that are basically the size of Jupiter. This is what ultra-cool dwarf stars are. And they are found using the transit technique. And then we can get to their masses using what's called the transit timing variation. I mentioned that they are found in a configuration that's basically an astronomical Swiss clock, because they are tightly packed all together, and yet they are found in a stable system, a system that survived 8+ billion years. And that's due to the fact that they are all in resonances with each other. They turn around the star, tugging in one direction, tugging in the other direction. It just stabilizes the system. And that leads to slight variation in the timing of the transits, which gives us information about their relative masses. And then we can get the mass of all of them. So it's another way to get the mass of the planet, tidal interactions. OK, I'm going to take your question. And then I think, yeah, go for it.
So you said that the presence of water could basically transfer the CO2 into the water as acid. I'm asking the question, so if, say, a planet had water, like Mars, but it instead froze over, would the CO2 method still work for that case or no?
Great question. So this is a situation that will be close to snowball Earth, right? So Earth has been through phases where the temperature dropped low enough such that it will be just covered in ice, stopping the water cycle, right? And so what happened is that there's a great feedback loop where volcanic activity doesn't stop. And so all of that carbon that is sequestrated inside the mantle and the crust, that's where most of it is. We could not just use ocean, by the way. For this to work, we really need to have active plate tectonic. That carbon that is stored inside comes out through volcanic activity, leading to greenhouse effect increasing and allowing us to leave the snowball Earth. So that's how it works out. So yes, the CO2 would end up leaking out and allowing for the planet to leave this phase of being completely frozen. Okay? Great questions. So if that's okay with you, I'm going to move on, and whatever question you have, you can keep it to the end. And now we are going to talk about detecting and managing our small neighbors, decameters neighbors, so objects that are in the 10, 100 meter size. And believe it or not, to talk about that, I'm going to go back to this chart, because in this chart, there's an interesting bit that relates not to doing transmission spectroscopy, but to doing emission spectroscopy. Emission relates to observing the light coming from the planet itself. We all radiate radiation. We all have about the same temperature, so we radiate the same kind of light. And we do use this technique to measure the actual temperature of planets. Why? Because when we search for atmosphere, if those planets have an atmosphere, the atmosphere is going to be able to capture the light, translate it into heat, and then redistribute the heat around the planet. And so a bare rock would have a very different temperature distribution than a planet that have an atmosphere, absorb the light, the heat, and then redistribute it. Okay? So some of the work we've been doing, including with the TRAPPIST-1 system, has been leveraging this. Now, if we are looking at temperate planets, they are bright in the wavelengths or color regime where Earth is bright, because where you're bright in the wavelength space is really defined by your equilibrium temperature. That's black body radiation. Now, guess what else is bright when we're looking at TRAPPIST-1 all the way out there? Anything in the solar system from Earth to Jupiter. What you see here is the brightness distribution, basically, as a function of a distance. 1 AU is the distance between Earth and the Sun. You have a first peak that relates to the sunlight that you are reflecting. And then you have a second peak, much higher, that relates to your own thermal emission. Okay? So this wavelength range between 10 to 20 micron is what we use to observe TRAPPIST-1. And as we're observing that, we're also really sensitive to, again, anything between Earth and Jupiter. So what we did, we took all of the TRAPPIST-1 data that we had to study, again, these planets, and realized that there's a bunch of things that are just crossing our field of view. Asteroids that were known, bright enough to be seen on independent images. And then when we were doing a technique that's synthetic tracking, let me actually explain that. Synthetic tracking, 2 steps to this explanation. You have your phone, and you do a long exposure. What happens? The details that are just faint in the background shine through, right? Now imagine you want to reveal a firefly that's flying. You would have to take your phone and basically follow the firefly while doing your exposure, right? That's active tracking. Synthetic tracking is doing that without knowing how the firefly has been moving and shuffling the images in all possible directions and seeing as the firefly shine through. It's basically integrating your images. That's what we do here with asteroids. We're asking ourselves, if I shuffle these images in that direction, assuming an asteroid was going in that direction at that speed, do I see something shine in the noise? Okay. It's computationally expensive unless you have access to GPUs, which is now possible because they are quite cheap. So we use that and the fact that these asteroids are really bright in the infrared to reveal unknown asteroids, and importantly, the smallest ever found. And what I mean by smallest ever found, that's what we're looking at. Humanity has been sensitive to main belt asteroid down to about 1 kilometer. That actually is a mandate to NASA from Congress, because 1 kilometer size objects are extinction level threat. So Congress required NASA to find all of them. And we brought that sensitivity from kilometer size all the way down to decameter size. These were the objects known in the kilometer regime in our data sets. And then for free, we showed that we could find objects all the way down to 10 meters, humanity knew that there was about 2 million objects of 1 kilometer and above inside, and we showed now that there is in the main belt about 10 billion asteroids from 10 meters onwards. And most importantly, we revealed this kink in the size-frequency distribution that shows a transition from different types of regime to collision-driven regime, breaking any objects from 100 meters down in size into small and small rubble really efficiently, creating a pool of asteroids that can move from the main belt population to the near-Earth objects. That's basically where they become meteorites. Okay. So why is that important for planetary defense? It's cool for asteroid science, but for planetary defense, we've been sensitive to near-Earth objects or potential impactor with ground-based facility when they pass close to Earth, and now with this, we're sensitive to them basically anywhere. Quick proof of concept. Literally 2 weeks after we published our paper, and in that paper I made sure that we said that James Webb is an asset for planetary defense. Guess what? Humanity found 2024 YR4, the first asteroid in a while to score 3 on the Torino scale, triggering United Nations protocol and so forth. We turned to NASA and told them, hey, we think that's something we can do something about. So we got to turn JWST here, to the asteroid, assessed its size, reported that in a memo to the United Nations, 60 meter. And then in the meantime, people relaxed. Why? Because the cone of probability of the asteroid, which was here back in February, started to narrow as we were gathering more and more measurements and moved away from Earth. And planetary defense protocols that have been put in place really only care about Earth. Which got me thinking, wait a second, it's a small thing, but if it hits the moon, is it really something that we shouldn't care about? And that was before this happened, by the way. Back of the envelope calculation, 60 meters, that leads to a 1 kilometer crater of the moon. That's about 100,000 tons of material being released. It's a lot for our fleet of satellites. I mean, our whole economic system, actually industrial, social, communication, GPS, military application rely on a $500 billion fleet of satellites. So if it were to go for the moon, that may actually be a problem. Fast forward in June, where the cone of probability started drifting to the moon. And then this kind of thing started to come up, CNN and so forth. So in the meantime, we started this education process, because again, planetary defense only focused on asteroids that could impact Earth. And move forward with another approach, really educating people about the fact that a 60-meter class object impacting the moon is more consequential than a 60-meter object impacting Earth, because the atmosphere will be protecting us mostly. I'm going to skip the simulation because it's not really relevant. And lucky you, we found a window in 2026 where we could observe that asteroid. So wait, by March, you will know if that asteroid is actually going for the moon in 2032. And these 2 additional years, because yes, current facilities from the ground can only redetect these asteroids in 2028. So by moving forward in 2026, we're buying you and the UN 2 years to decide what to do if indeed that thing is going for the moon. Great. So that's for planetary defense. And I realized we put in the room that it might be interesting to talk about business. And I'm talking about space treasure in the last slide. So I've said we use GPUs. Some of the GPUs we use were actually provided by NVIDIA through a grant, so we can thank them for that. But I also wanted to mention NVIDIA to provide you with a reference frame. NVIDIA today is the highest value corporation, $5 trillion since last week. Let's keep that number in mind. I believe that space, through the potential of exohabitat, that's more inspirational, but practically speaking, through space resources, is going to drive a new industrial revolution. Why? Because these asteroids can be worth an incredible amount of money. And of course, money is a construct that will evolve over time. But let me put this into numbers. Psyche, an asteroid to which we're flying a mission, is worth 10,000 quadrillion dollars. That is 10 billion of billions of dollars. If you like zeros, that's what it's worth. if you want to think in terms of NVIDIA, the largest corporation, it's 2 million times the worth of NVIDIA. Now, why is that important? Not only because it can provide access to a whole new market. I'm talking here about multi-quadrillion, if not quintillion, and that's something that we have to talk about because obviously if you bring something that's worth that much money, the value of it changes the whole economy. But also, and most importantly, one of the challenges we're facing now for growth relate to accessing, elements that are tough to mine. It has strong implication for our environment. And so moving mining into space can alleviate that problem, and most importantly, yield to resources in space that can be moved directly to the moon or to Mars without having to lift them up from Earth. And so that really is one way to move past some key bottlenecks for becoming a multi-planet or interplanetary species. So back to the class. In the class, of course, we look at where we got here, but also, and most importantly, where we're going. And I think what we're going or where we're going is in space, and very, very soon. So I hope you got excited through this journey. I'll leave you with my takeaways, and I look forward to the next round of questions. Thank you. Yeah.
You describe all those exoplanets. About how far away are they, say, in light years?
Yeah, so the closest one I found around Alpha and Proxima Centauri, and that's just a few light years away. The bulk of them are found in the hundreds of light years away. But we had a discussion around dinner. I would not be too concerned about distance. I think our concept of space and time are likely to evolve quite a bit in the next decade. So it's close enough.
Are they mostly looking toward the center of the galaxy, away or along the...
They are mostly in the plane. The bulk of them are toward the center because that's how the Kepler mission, which found most of them, was designed. And those are further away. The ones that were found by Kepler are further away, so not necessarily of interest for the search for life. But basically at this stage, consider that there is planets everywhere, even not around star, back to the free-floating planets I discussed before. I'll take questions from people that I haven't asked question yet, and then I'll come back. Yeah. No, you haven't asked question yet.
Yeah, so with billions of cell phones that we have, and they're all broadcasting on a small set of frequencies, but different phases and different amplitudes, does that look like noise or does it look like intelligent data?
I mean, it depends how you're asking the question in the sense of, does it look like noise to us, or does it look like noise to us 10 years, 20 years, 30 years into the future?
People on TRAPPIST, they have...
Yeah, so the people on TRAPPIST may have been there for a few billion years more than we do, right? The system is 4 billion years old. Now think about our technological development in the matter of 2 centuries. Now think about where we'll be in a few billion years from now. I'll be surprised if any advanced civilization will be bothered by this noise. I think they'll be able to understand what that is without any problem. So that's what I meant by if we are looking at it, maybe it will be noise and will not capture what it means. But if it's us 10, 20, 30, 50 billion years into the future, then I think we'll be able to make sense of that and understand that there is some life form. And by the way, the easiest way for us to assess if we are a habitable or inhabited planet is complex molecules such as CFC, right? CFCs have been in the atmosphere. There's no way a planet will produce complex molecule like that. So that's clearly a technosignature. So if someone were to look at us in spectroscopic work, they would see complex molecule in our atmosphere and definitely know that we are an advanced species to some extent. It's not just a pool of bacteria. We've been through an industrial age, at least, to produce this kind of molecule. Mm-hmm.
Are you able to detect your analysis the relative differences in the densities of the atmospheres of the exoplanets? And in general, is the magnetic field necessary to maintain significantly dense atmospheres around such planets?
Great question. So the first part of the question relates to how dense an atmosphere is. And I think even that can be broken down into 2 layers. On the one hand, it's how how much of an atmosphere you have and what is the pressure level, right? So for example, Earth versus Venus. Earth is 1 bar at the surface, Venus has 100 bar. And that relates to the fact, again, that all of the carbon dioxide that Earth has sequestrated went back into the atmosphere for Venus. That's why there's such a thick atmosphere. That is something that we cannot do with the current technique. We can do that in emission. Transmission doesn't allow to probe as deep as emission. So transmission typically cap at understanding or probing down to 1 bar, not much below. Emission can go below, so that's the first layer of answer. The other level of the question is, what is the mean molecular weight of the atmosphere? Is it mostly an atmosphere that's made out of light elements, like hydrogen dominated, or something that is made of elements that are more heavy, CO2, for example? CO2, the gas of CO2 for the same volume is about 20 times heavier than hydrogen for the same volume again. And that is something that we can easily constrain because that shapes the whole pressure profile of the atmosphere. So we can easily constrain what is the dominant compound or component in an atmosphere, yeah. So that's for that. And then you had a question with regard to, I forgot the other part of your question, sorry.
Magnetic fields necessary to maintain such
Yeah, so the best way to maintain an atmosphere is through the gravity of the planet. That is the reason why Mars lost it, even though Mars actually was also eroded most likely by interaction with the stellar wind. So if you have a planet that's dense enough, you can hold on to low density atmosphere, like hydrogen atmosphere. Terrestrial planets cannot do that, and so they tend to lose those gases. So you don't necessarily need the magnetic field. There's a way to reveal magnetic field, and that's through another level of complication with regard to spectroscopy. You can look for Zeeman effect in this kind of way, or magnetic reconnection. That's usually not the kind of thing we do. That's it's like next generation mostly. Okay. So fortunately, planet can hold on to that without magnetic field. It will be my key answer here. Just like Earth can hold on to it. So let's see. Anyone has another? So there's 3 people that want to ask questions. Yeah. That I've already.
Are the budgeting policies of the new U.S. administration affecting the speed of this research, or will it?
Affecting the speed of this research. I'll say most of the research that's ongoing right now is fully funded. So that's a politically correct way to say no. But, you know, the extent to which astrophysics research is as sensitive as planetary defense research, for example, is pretty obvious. So I'm not going to lie. One of the reasons we diversified our portfolio and moved towards planetary defense and even planetary resources is being understanding that, you know, astrophysics may not be the golden goose in the years to move forward. All right, let's go. I'll get to these 2 and I'll get to you after, okay? Yeah.
Oh, my understanding is with NASA, they plan to go to the moon before 32. And they were looking at north and southern pole, I understand. But in December 22nd, 2032, that's more than just talking about satellites. You know, we're talking about actual colonies on the moon, whether it be Chinese or American, on either side. That would seem to be I see where you're coming from. That truly would be defense, planetary defense, yeah.
There'll be planetary defense, but it will still be local, right?
How soon would they know they have to either leave or
you
don't know where it's going to hit? It's just like a hurricane, you don't know.
Yeah. Yeah, totally. And that's really why we managed to convince them to just move forward quickly with that. This is the only way to have an answer before 2028, is by us doing that observation in March 2026. And then from there, we'll make the decision.
So that's a real aspect.
That's a tangible aspect, but honestly, that's nothing compared to the impact on our $500 billion space fleet, right?
Right.
Like, we're basically looking at, so every satellite is designed to go through a certain amount of micrometeorites. If this happens, again, only 4% chance at this stage, but we'll refine that. If this happens, the amount of micrometeorites our satellite will be facing in a matter of just a few days is equivalent to what they will be actually exposed to over the course of more than a decade. So that's the influx of micrometeorite, and I'll let you imagine the consequences. Debris from the moon coming into cislunar space.
Antarctica will find a lot of
Yeah.
moon rocks, eh?
We had a question over there. No, from you, yeah.
I know, like, I get that these planets could have life and may be habitable, but what I'm saying is this: even if they do have water on them, who knows? I mean, our planet is very, very unusual. So this makes me wonder if the worlds that we think of as habitable, the ones that have all the conditions for life met, might not have it.
Yeah, so the point that's made here is that having water may not be sufficient for life to emerge, right? And that's when we enter the realm of belief, because again, we have only one sample, Earth, right? My belief is that life is really nothing special. Life is just a continuum of more and more complex processes. We, human beings, like to put things in a box. There's the processes that happen at small scales that we call physics, and then at some point they complexify and we draw a line and we call that chemistry. And then it keeps on complexifying at different scales and then we draw a line and we call that biology. And then these processes become like more and more meta level and we call that intelligence, and then I don't know what comes next. But the point is that if there is water, water is such a great solvent for a bunch of chemistry to happen that it seems, with that perspective of mine, that what we would call life would actually emerge on its own. Now the cool thing is, and I mentioned Venus and no one is going back to Venus, the cool thing is that we are now getting to a place where we appreciate the fact that there could be other solvent than water. And that's an interesting question. Like, why are we looking for water? Because we know that water is a good solvent, life form emerge from it. But Venus has sulfuric acid. And we talk about Carl Sagan. Carl Sagan postulated in the 60s that there could be, before we knew that there was sulfuric acid in the atmosphere of Venus, he postulated that there could be life forms that are floating in the atmosphere of Venus, moving up to get energy from the sun, moving down to feed from the carcass, still floating in the cloud. I mean, I guess you don't know, there's a bunch of bacteria floating in the air all the way up to tens of kilometers in the atmosphere, so there's a lot of nutrients. And so his idea was the same was happening in Venus. That died off when people realized that there was sulfuric acid. Now guess what? We have the Morningstar mission going to Venus now because a few years ago, phosphine, a gas phosphine, was detected in Venus, and there is no way on Earth we can explain that without either industrial processes or life. And so now we're getting really excited because Venus, who was forgotten for a while, with big focus on Mars, is actually the place where we could still find active life form. Why? Because people are now showing that in sulfuric acid, a wide range of complex chemical reaction can occur. And sulfuric acid, which is not a viable solvent for us, don't try putting your finger in there, is actually viable to other form of chemistry and potentially completely different life form. So it could be, that's where it gets exciting to me, it could be that we're looking at the solar system in such a way that at some point in the past, Mars, Venus, and Earth were habitable. We do know that there is interplanetary transfer. We do have material coming from Venus, meteorite coming from Venus, material coming from Mars. So it could very well be that at some point the whole solar system was sharing a tree of life. And if we find forms of life in the clouds of Venus and sequence the DNA, it could very well be that there will be some overlap and there was horizontal gene transfer across the three terrestrial planets of our solar system. And some of our ancestors managed to evolve and become life form in sulfuric acid. That's what could be for the next 10, 20 years. Yeah.
So are there any techniques to determine length of day on these exoplanets, and how does that compare to the length of day on Earth?
Awesome question. So length of day is typically just the rotation period, right? How long does it take to the planet to turn upon itself? I'm sure you've all noticed that the moon always shows the same phase to Earth. That's because the moon tidally locked, meaning its rotation period became its orbital period, right? When we have systems like TRAPPIST-1, I'm trying to find the slides, they are so close. Actually, most exoplanets that are orbiting their star within 10, 15 days we believe that they also become tidally locked, meaning that they are always showing the same face to their star. Okay, so they have a permanent day side and a permanent night side, which is why if you look at TRAPPIST-1F, it is represented here with a frozen night side and a liquid day side. So for those planets, the length of the day is basically the orbital period. So for this planet, the orbital period ranges from 1.5 days, that's the length of the day, to about 20 days for TRAPPIST-1H. Now the cool thing about that system is because it's so close to each other, it's literally like I've shown in this poster. From the surface of one of them, you would see planet passing by every few days that will be bigger than our moon. So think about the pull, this pull of space if life emerged on one of them, and you can start seeing, city lights or something like that from the surface of one of those planets. So I can imagine they would go into space far faster than we have.
So sort of the two detection methods that we talked about, it seems like both of them would require a pretty narrow window of the orbital plane reference to our line of sight. Do we have anything else in the works where we could see something that has an orbital plane that's normal to our line of bearing?
Yeah, that's a great question. So the next step, so the next generation instrument to detect exoplanet is actually what we call direct imaging. Because as I said, those techniques are indirect, right? We see the effect of the planet through the Doppler shift on the stellar spectrum. We see the effect of the planet on the stellar light because it blocks part of the light. The issue is that seeing the light from a planet is about the same as, imagine you have binoculars and you're on the East Coast and you're looking at a lighthouse on the West Coast, literally in terms of orders of magnitude. And the lighthouse is a star, but what you want to see is a firefly next to the lighthouse. You need really, really good optics and techniques to mask the lighthouse to be able to see the firefly. And that's direct imaging. So the next generation of instrument is doing exactly that. They find a way to mask the star so that we don't need the planet to be aligned, and we can start revealing them around. And that will allow us to have a less biased sample. So within the next 5 to 10 years, the bulk of exoplanet found would be through direct imaging, to answer your question.
We only use James Webb though, right? So that's one source.
James Webb is used. There is to date, a few dozen systems that have been revealed through, but these systems are very special in the sense that these are, because we have not refined direct imaging, we need the planet to be far away from the star, and we need them to be quite bright. And so the only system we found that are directly imaged are with gas giants far from their star and really young. Because when gas giants are really young, all of the gravitational energy that they harness when they gather their mass gets transferred into, or translated, converted into heat. So those gas, Jupiter is 100 Kelvin or so. Those gas giants are actually still hot, so still bright. And if they are far enough from their star, we can detect it with the current, basic version of direct imaging.
Let's have one more question, and then the speaker is more than happy to talk to you one-on-one.
Yeah.
So correct me if I'm wrong, but I think you said we might be able to find habitable planets that aren't in a solar system and just traveling through space. How does that work without a sun? Is it just geological heat or what? Maybe I misheard you.
No, totally right. Okay, so let's talk about those free-floating planets. Those free-floating planets are thought to primarily form during the formation process of a planetary system. They may be able to form on their own through collapse, just like we form stars, just like failed version of stars. But it's believed that during the formation process of a planetary system, we form planetary embryos that are basically between the mass of 1/10 of Earth to 10 Earth masses. And they have to tidally interact in order to, at some point, collide and form the final planet. In that process, there will be a lot of mishaps where they almost collide and merge, but they actually swing by, transfer energy, and one of them gets ejected. So there's a large fraction of the planet that should be in a planetary system that actually end up being scattered across space. That's to explain how we think a lot of them are formed. Now, remember I've talked about the reason why I had to point Hubble to TRAPPIST-1 early on? Because primordial atmosphere are really good greenhouse gases. That is what makes them habitable for a long period of time. if those planets, or they do exist, when these planets are ejected, they will be able to hold on to these hydrogen, helium atmosphere for a long time, which are really great greenhouse gas effect, or which have a really good greenhouse gas effect, which means the internal heat that they have gathered through their formation plus through radioactive decay will be shielded. And so they can keep potentially habitable temperature for 1 to 2 billion years. So without star, they could allow for life to emerge. And one of the theories for the emergence of life on Earth is in deep thermal vent in the ocean, right? No sunlight, just thermal heat. So it's not impossible that some of these free-floating planets may harbor life on their own without having a star.
Okay, well, let's thank the speaker again, and feel free to come down.